Okay, so just said we're trying to we'll go through energy types and what is energy and do some stuff today here. So started the recording late. So the energy types thing, I'm going to open up slides. We'll go through just a very small portion of the slides that are available here. We'll do those for a little bit, and then we'll actually spend some time on the assignment that you have for today. So by the end of our half hour, you should be hopefully about done with the assignment that you have scheduled for today. And then after that, you can go through and take a look at any missing homework that you might have from previous days or weeks. So let's see, hide that. Need to get this thing back again. Clicky. Um, and I'll still. Um, presenter view. So this will still be loaded up in a way where you can ask questions if you have them. You can ask them anonymously. I'm getting ready to pull up um, the tools so you can ask those questions. It takes me a second to get there. Copy this. And then I'm putting the link for questions in the Google Meeting chat. So um, that is the link. You also see the text on the top of the screen there, but that's the link in the Google chat where if you have questions, you can ask them. Remember, you can check the box to make them anonymous and all that good stuff. So here we go. Okay, so energy types, energy conservation, we're just going to get a very small portion of the way through this for today. So uh, energy, there are a few things that are kind of tough to describe. Energy and money are kind of alike. Um, we describe them not by what they are, but kind of by what they do. And I guess a lot of things are kind of like that, right? If you're going to describe a person, you say, well, they're nice, they're funny, you kind of describe some characteristics or traits. Well, if we're going to talk about money, all right, aside from one word definitions, give me in the comments thingy here, in that slides link, um, give me an easy definition for money. Just something off the cuff. What is money? So examples of money would be like a dollar, a quarter. But what is money? How would you define money? Nobody's typed anything in yet. A value. There we go. With a value that can be used for trading things. That works. Uh, a current medium of exchange in the form of coins and banknotes. Coins and banknotes collectively. That looks like somebody might have Googled it. Well done. um, so those currency, another a good clean one word, one word one. The issue that we often have with energy and a description for energy is the same issue that we have with saying money and currency as a definition, right? Because if somebody says, what is money? And you say currency, and then they say, what is currency? Well, it's money. And we kind of get this circular definition going. And a lot of examples for definitions for what energy is, a lot of people will say, what's energy? Or if you look up energy, the answer will be, it's the ability to do work. What is work? The transfer of energy. And we kind of just get this, it just goes around and around and around in circles, just like you could go around in circles with money and currency, money and currency. So um, uh, Koichiro mentioned that money is a value that can be traded for things, or something that can be traded for things. So we're talking about what, excuse me, there's an example of saying what money does, like what you can do with money. Well, if we take the same approach with energy, when energy is transferred, we can change the speed of something, we can change the height or location of something. If we transfer energy, we can change the temperature of something. If we transfer energy, we can change the shape of a system, bend it, break it. If we transfer energy, we can make something brighter or less bright. All of those sorts of things are examples of what you can do when you transfer or trade energy. Just like you can transfer or trade money for, you know, a nice pair of socks or whatever, right? Also, the last one there, if you transfer energy, you can make a system go through a chemical reaction, or you can change it. You can have a chemical reaction proceed. So I think it's useful to talk about energy as what it does, um, because yeah. Well, I think that's that. We'll stop there. Um, all right, come on, click A. There we go. So this one, there's a version of this that's in your slide, or pardon me, not in your slides, in the Google form that we go through and we'll talk about today. And this should kind of bring back some of the thoughts that we have off of the energy skate park thing that we did last week, where we had that skater going up and down and we were looking at the bar chart. So kinetic energy, it depends on really two things. It depends on the mass of the object, and it depends on the velocity of the object. Those are the two factors that kinetic energy depends on. So if we're trying to figure out, oopsies, pardon me, if we're trying to figure out if something has kinetic energy, the evidence that we look for is that it's moving, that it has a velocity that's not zero. And we usually compare that velocity to something stationary, in the room or nearby. So the evidence that there is kinetic energy, there's an object that has mass, and we see it moving with a velocity that's not zero. So when we're trying to figure out what types of energies are present for something, kinetic energy, is there a thing? And does it have a velocity? Is it moving? There you go. Then it must have kinetic energy. Um, the way we calculate kinetic energy, in a normal school year, we would go through and we would try to kind of show where this equation comes from, because it looks pretty strange, right? I mean, where do you get 1/2 and why do you square the velocity? There are experimental reasons for that, but I think right now with where we are, it's simplest, maybe not most comfortable for you, but simplest if we just say, hey, kinetic energy, what type? Kinetic, down there. Kinetic energy is calculated by saying 1/2 the mass of the object in kilograms times the velocity of the object in meters per second, I guess. And we square just the velocity. We don't square the mass. We don't square the 1/2. We just square that velocity. In equations that we do, I usually try to say big E for energy and a little subscript note down below for kinetic. So E for energy, kinetic. But if you go and you do some Googling, it's pretty likely that you will also see KE for kinetic energy. So um, just so you know, if you're going to look for other sources of information, you might see that. Units of measurement for energy. All energy is measured in something called joules, capital J. Um, and we can break a joule down. A joule is the same thing as a Newton times a meter. Not a Newton per meter, but a Newton meter. We really want to avoid the per there. So it's Newton meter, which seems strange, but it's the way it is. You start to get used to it after a while. So a Newton meter, or newtons are a measure of force, meters are a measure of change in position. So if we have force applied to change the position, that is also a way to look at energy. But Newton meter or joules are the units of measure for this. I'll make these slides available also later. So if you want to take a look at them later, you can use that to double check some things. And then there's one more slide that I want to look at, and then we'll go to start looking at and working on today's assignment. So next slide. Clicky. There we go. Gravitational potential energy. A lot of folks, when they're in like middle school or earlier grades, will just say potential energy. but really there are lots of things that end up being referred to as potential energy. There's this gravitational potential energy. There's energy stored in an elastic or stretchable object. So some people will call that elastic potential energy. Uh, Energy that's included in some of the chemical reactions that we see, people will sometimes call chemical potential energy. So it's really important that we get gravitational on there. And if I drop anything out of gravitational potential energy, I usually drop the word potential and just call it gravitational energy, because it is energy there right now. Potential sometimes gives us this misleading feeling that it's possible for it to have energy, but that it has energy. Gravitational energy is present as energy right then. So the word potential, I feel, is misleading. Uh, I'm not alone. So gravitational energy is really what we're looking at. And gravitational energy, again, when we had that energy skate park guy or person, because you could change it different things, or at least you used to be able to. The gravitational energy depends on the mass of the object. A more massive object has more gravitational energy. It depends on the height of that object to compare to. Sorry, excuse me. The gravitational energy depends on the height of the object compared to some place or some position we consider to be zero height. Um, and it depends on the gravitational field of the Earth, and the Earth must be included. Like if we're doing a system schema, uh, the Earth would have to be in our system for there to be gravitational energy. And then the reminder that just like when we did weight, G on Earth, again, 9.8 newtons per kilogram. So if we have an object and we're trying to figure out what types of energies are present, if it's kinetic, like we said on the previous slide, we would say, hey, there's something moving, there's an object that has mass and it's moving, it's got some velocity. If we're trying to figure out if gravitational energy is present, well, then we say, well, there must be an object there that has mass. There must be some height that's greater than zero, or a height that changes throughout the motion or throughout the scenario. And it would have to be on Earth or some other planet type thing where there's a gravitational field. And so on this one, the equation is a little bit more simple. No one halves, no squareds. It's just the mass of the object in kilograms, G, 9.8 newtons per kilogram, and H, the height above that 0 point, and that should be in meters. Good. And then if you go Googling gravitational energy, you will see a lot of places refer to it just as potential, but you need to be careful because it depends on the sophistication of the website that you're looking at. Because sometimes some websites will talk about potential as like this category of energies, and they'll include a bunch of different subtypes like elastic and gravitational and chemical and all these other things. And some will use it rather flippantly without discussing which type we're looking at. Um, you will often see if stuff is geared towards like eighth, ninth grade, you'll often see it as GPE for gravitational potential energy. You might see it as PE. If I just saw it as PE personally, as I was looking through for resources, if I saw it just as PE, I would probably go to a different website because that's a sign that it might be geared a little bit below where we're at a younger age group. But either energy, what type, gravitational, big E, subscript note G, or GPE for gravitational potential energy. Units of measure, a Newton times a meter, or a joule, capital J. And that's named after a person, a guy that way back in the day did some studying on energy and temperatures and liquids and things like that. Excuse me, he actually uh, was it beer or wine? He was like he brewed or made either beer or wine, and the temperature of the slurry that he made was or that he needed was a fairly specific thing, and he came up with the relationship between the ability to like stir it. If you stir it in a certain way, you can increase the temperature, and so this Joule character. Had a lot of stuff to do with that. Weird side note, on his honeymoon, he decided to take his wife to a big waterfall. I don't remember if it was Niagara Falls or not. Like, big waterfall because, oh, it's beautiful, romantic. No, he went because he wanted to see if the temperature of the water was different at the top and the bottom, because he was thinking that there would be an energy transfer due to this change in height. So he wanted to measure the temperature of the water up at top. And then as it fell down and then hit and collided and swirled, he figured there would be a small temperature change. Turns out he was right. Happy, congratulations, way to go. Bet that was a great honeymoon. That's either an understanding wife or a short-lived marriage. But uh, it is what it is. So that's the stuff for these slides that I wanted to go through, right? Gravitational energy. Evidence that there's gravitational energy is that there's a height that's greater than zero. There's an object, it's in a gravitational field. The equation, mgh, mass in kilograms, g, 9.8 newtons per kilogram, h, height in meters. The previous slide, just a quick review, kinetic energy, evidence that there is energy, kinetic energy. There's an object that has mass, and that includes even like air has mass, right? Um, so an object that has mass and is moving. And then the equation for kinetic energy, 1/2 times the mass in kilograms, and then the velocity squared, but just the velocity squared, not the whole thing squared, just the velocity. Okay, dokie. All right. So we have 10 minutes left. To me, I'm gonna switch over to uh, the assignment today. So we can start to go through these. 4 people have it done already. Lord. Um, Good for you. So this is one of the assignments. It's in Google Classroom, right? So if you go here, and you just click on 0121, that's today's date, energy types, conversions, and equations. If you click on that and you open up the form, hey, that'll be this. What a deal. So I'm just planning to go through, we can kind of talk through, see what we have, and make sure that everything's good. Oh, I missed a comment like 5 minutes ago. Sorry, Anonymous. Wouldn't all objects on Earth have gravitational potential energy because gravity pulls things to the center of the Earth? And when things are on the surface, they are still pulling towards the center. That's a really good question. Thanks for asking. I'm going to give that a thumbs up. Thumbs up, kid. It won't let me. Let me. Let me. It won't let me. All right. Well, maybe it won't let me. Maybe it might let you. Hey, so all objects would experience the gravitational field. So this person is saying, would all objects have gravitational energy? And that's a great question. They would all experience the gravitational field. They would all have a weight or a gravitational force acting on them, pulling them down. But remember, the last thing is that height deal. And so, like, if this mug is sitting on the table, and I'm saying for this problem, I would be saying that like the table is zero height. Well, then, if for this problem, looking at the mug, the table is zero height, then the gravitational energy would be zero, m times g times h, height above a position that we consider to be zero. So we have to choose where zero is for a problem, and we stick with it. So for this like mug scenario, the mug is on the presence or in the presence of the Earth. There is a G, there is an M. But now for this problem, if I say this is zero height, well, then there's no gravitational energy here. There is still a field. It is still being pulled down. But just because something's being pulled or pushed, that doesn't mean there's energy. There is a force, yes, but not necessarily energy. Yeah. Now, if we say, okay, we change it a smidge bit, and we say, okay, now the mug is there and the height, zero height is here. Well, now it's at a greater height. If I choose this to be zero, now this has a potential energy, a gravitational energy that's not zero. But for every problem, we can choose where zero height is. And that's a really useful thing because it turns out that the more important thing, the more significant thing is how much that energy changes over time. So if we choose where zero height is, and generally we choose for a given problem, it's easiest if we choose the lowest position that the object is in throughout that problem. So all objects on Earth would experience the gravitational field. They would all experience a gravitational force, Earth on that object, but gravitational energy would depend on looking at that object and determining what zero height is while you're studying that object. I hope that helps. Wait a minute. See if anything else pops up. So I'm going to go through and start looking at this, and we can see what we've got. I kind of have to answer stuff. Last name, Lulai. Oh, I'm editing the question right now. There we go. I forgot from here. How do I? Maybe I'm not. Am I not entering? Why? I don't often. Here, we'll do this. So I'll do that. There we go. Okay. You guys see the form here? Yeah. Okay. Cool. Um, where did my mouse go? Mouse. There you are. So if I don't type in answers, it won't um, let me move to the next screen. So this is like from the slides that we just looked at, this energy is thing. This was in case we didn't do this in class today. So the same sort of thing, describing what energy is. And then this is a summary of the idea of kinetic energy, including the equation. We need to have mass in kilograms. We need to have velocity in meters per second. Then to calculate kinetic energy, it's 1/2 times the mass times the velocity, and the velocity squared, not the entire thing squared. So if I go down and I'm going to take a look at this, you can pull out your handy dandy calculator and see what you get. If I pull my calculator up, do you guys see the calculator on my screen or no? No. All right. Um, let's see. We'll try. I don't know how long it takes to load this one. This is my new favorite online calculator. Um, all right. Okay. Uh, so let's see. I need to double check what numbers we had. So we say we have a person riding a hoverboard. The combined mass of the person and the hoverboard is 70 kilograms. They're going 3 meters per second. What's the kinetic energy? 70 kilograms, 3 meters per second, and that's our equation. So 1/2 times the mass times 3. So if I go over here, I could say zero 0.5. Can you see that at all, or is that way too tiny? You can see it? Okay. So I do zero 0.5 times the mass, and the mass was, I believe, is it 70 or 75? 0 or 5? Thanks, guys. Times 70, and then times 3. The velocity was 3, and then we need to square the 3. So we could do times. So there are a bunch of ways that we can worry about PEMDAS and things like that. For me, the cheap and easy way sometimes, if I forget to put parentheses in or something, the cheap and easy way, it's times 3 squared. So I'm just going to go times 3 times 3. Your math teacher might go, but they can settle. And then we hit execute. 315. That's what I got here. Let's see. Cross your fingers. Haha, that is an answer choice. Victory is mine. You with me there? Some head nods. I'm doing this for me. I'm getting points doing this myself. Make sure you're doing this for you, so you get points for yourself, right? Um, So that's an example for that one. And now this one, next one, we're still talking about the hoverboard, but now we say they're giving their friend a piggyback ride. They have a combined mass of 140 kilograms. They're still going 3 meters per second. So we can go over floop, floop, uh, 0.5, because it's always 1/2, 1/2, and 0.5 are the same thing, times. And now they said the mass increased to 140 because they're being reckless and giving somebody a piggyback ride. So times 140. And then times velocity squared. The velocity is 3. I can also say, hey, 3 times 3 is 9. I can just put times 9 in there. Execute. And there I get 630. Okay. So now, I go back here. The kinetic energy, 630 joules. Victory. Winning. Mm, mm. All right. Now, the person riding the hoverboard, they have a mass of 70 kilograms. They get rid of their friend, ditch them. They found a way to change the gearing on the hoverboard. You be careful, kid. And now they get it going an amazing 6 meters per second. Hold on. That's fast. What's fast for a hoverboard, actually? What's the kinetic energy of the person in the hoverboard in this circumstance? So now, if you notice these first two, we went from 70 kilograms to 140 kilograms. So these first two, we doubled the mass, and we went from 315 joules to 630 joules. We doubled the mass. We doubled the kinetic energy. Yeah. This next one, now we're going back to the same mass, but now we're doubling the velocity, right? So we'll see the effect that that has. And as I look at the time, it's 9:30. So if you want to bail and head, you can. If you want to hang out while we continue to go through these, you can hang out while we continue to go through these. That's fine by me. I understand. Time is what time is, and you might need to move on. And there are 4 or so of you that already finished this. So hey, there you go. No offense taken for those that bug out. So have a good day, folks. Thank you. So now if for the rest of us, I'm just going to continue on with this one. So now if I say, hey, the mass is 70 kilograms and they're now going 6 meters per second, I'm going to go back and do this calculation. So now I can say, hey, kinetic energy is always 1/2 or 0.5 times the mass. And the mass in this case is just the person and the hoverboard, so that's 70 kilograms. And in this case, we said their velocity was now 6 meters per second. They putzed with the equipment and got it up to 6. So that gives us 6 squared, the velocity squared. And I hit execute. 1,260. So clicky, 1,260. You okay there? All right. And then as we move on, so now here we're saying, hey, we started with 70 kilograms and a velocity of 3. On one of these problems, we doubled the mass. On the other, we doubled the velocity. Which one had the greater impact, or were they both the same? So if we doubled the mass or doubled the velocity, which one of those had the greater impact on the amount of energy present? So when we doubled the mass, we went from 315 joules up to 630 joules. So we doubling the mass, we doubled the energy. And now if we go to 315 joules, that's the one that we started at. And then if we double the velocity, doubling the velocity got us all the way up to 1,260. A few folks have typed in their velocity. The velocity does seem to have a bigger impact, right? Because when we doubled the velocity, we ended up actually doubling. Pardon me. When we doubled the mass, we just flat out doubled the doubled the energy. When we doubled the velocity, we actually quadrupled the energy from 315 all the way up to 1260. Right. And now that seems a little bit weird at first, but then if we go back and we look at the equation, it hopefully makes a little bit of sense, right? We're just taking mass times whatever, and there you go. But the velocity, whatever the velocity is, we square it. So if we increase the velocity, we don't increase the energy a little bit, we square the velocity. So that has a much bigger impact on the energy of the car, or pardon me, on the energy of the object. Excuse me. So this is a spot where there are some science teachers, physics teachers out there that also do drivers training, drivers ed stuff. I'm not one of them. That's not my gig. But this is a spot where those folks that do drivers ed would say, so this is why it's careful to follow the speed limits, because if you as you increase your velocity, you're not just increasing your energy a little bit, you're increasing your energy a lot. And that has a big effect on stopping distances, bigger than one might think. So it turns out that doubling the velocity had a much larger impact on the kinetic energy than doubling the mass. That's the way I'd go. Next. I thought I hit next. There we go. Okay. So that's the one slide for, or the one part for kinetic energy. This part is for gravitational energy, and it's really going through the same process. So as we scroll through. So now gravitational energy, objects have, this is again is the same sort of thing that was on the slides, and we can say gravitational energy is m times g times h. Mass must be in um, mass must be in kilograms. G is that 9.8 newtons per kilogram, and then the height must be in meters. So we've got that stuff rolling. This back in the day when I was a kid, one of the late night talk shows was David Letterman, and he used to be on like later. He used to be the show that started at 11:30 after one of the earlier shows. And one of the things they would do, they would drop things off of buildings. So when I was a kid, I thoroughly enjoyed that. Um, and in this one, I think it's worth seeing. Come on. They have a bowling ball. Oops, a bowling ball and a. It won't let me full screen is under the. Oh, here, we'll try this. So they have a bowling ball out of a third floor window um, that they're going to try to that they're dropping in there. Uh, it takes a few seconds to get there. Um, they get there. I enjoy it. It seems like that might be more for me than for you, but I thoroughly enjoyed that. I'm okay. So I hope you truly did feel that. I enjoy that. He did other things where they would drop other stuff off the building, and they did stuff where they would have uh, where I steamroller. You know those road machines that just have the big roller that flatten down the road. They would have that drive over stuff. And they did a bunch of stupid things like that. So now a bowling ball has a mass of 5 kilograms. It's 3 floors above the ground, which is 4.5 meters. It's on Earth, so we have a G of this. Um, what would be the gravitational bowling, pardon me, what would be the gravitational energy of the Earth and bowling ball system? So remember, if we're going to talk about the gravitational energy of the ball, we have to say, hey, the Earth is included in our system. So the gravitational energy of the Earth ball system, we must include them both. So if we're going to go through and do that, we have our height, we have G, and we have the mass. And remember that the equation is just m times G times H. So need to remember what we had for those numbers. So M is 5 kilograms, G is 9.8, and our height is 4.5. So if I just go to my calculator, I was trying to clear. Oh, okay. So mass, 5 kilograms, times G, which is 9.8 newtons per kilogram, times height, which in this problem they tell us is 4.5 meters. So I get 220.5. So I go back here, 220. That's about as close as we'll get. Floop, floop. Okay. Scrolling on down, bowling ball is replaced with a block that has a mass of 10 kilograms, twice as massive as the first one, height of 4.5 meters, and still G of that. So just like the previous page where we went through and we doubled the mass of the object and then we checked to see its impact on kinetic energy, here we're doubling the mass of the object and going to check to see its impact on gravitational energy. So now we have a mass of 10 kilograms, same height, 4.5, same planet, Earth, same G, 9.8. So now going over here, I would say M times G times H. Mass is 10 kilograms. G is the gravitational field of the Earth, which is 9.8 newtons per kilogram. And then the height is the same thing, 4.5 meters. So then we're at 441 joules of energy. So there. 220 to 441, that's about double, right? And this was really 220.5. So we're right there. So we doubled the mass, we doubled the gravitational energy. Some folks are kind of slipping away and hanging up and moving on. That's fine by me. If you guys, we're down to like 10 of us here. So as you finish up, or if you're looking at this and you're like, hey, yeah, I'm kind of done, and Lulai's still talking, lordy, yeah, that's fine. If you need to move on, you can move on. We have, I guess, 2 questions left here. So now we're going back to the original mass, and now instead of doubling the mass, we're doubling the height, still on Earth, so G is the same. So here we're going to compare to see what happens when we double the height on these things. So M 5, G 9.8, and now our height is 9 instead of 4.5. So M times G times H, our M is 5 kilograms. Our height is 9.8 newton, or our G is 9.8 newtons per kilogram gravitational field. And then our height is 9 meters. Okay. And we get 441 again. 441. So now if we look at these, when we went from our initial settings and we doubled the mass, we ended up doubling the gravitational energy. When we went from our initial settings and doubled the height, we doubled our gravitational energy. So in this case, doubling the mass or doubling the height, in each case, we simply doubled the kinetic energy. So doubling one, doubling the other had the exact same effect, right? And that goes back to our equation. In the kinetic energy equation, it was velocity squared in there. And so impacting or changing the velocity had a bigger impact. Here, nothing is squared, nothing is square rooted. So if I double any one of these things, that's going to double the gravitational energy, just flat out. They all have doubling one doubles the end. So here we would say doubling the mass had a greater impact. No, doubling the height had a greater impact. No, doubling the mass and this had the same effect as doubling the height. So we should be looking at that. And then next. And that's thinking. And now this is just saying, hey, once you hit submit, you should be able to see your score. You should be able to see if we missed a question, and then you can go back and make a change and try to improve if we missed something. So that's we're about almost 15 minutes past, or 10 minutes, 10 to 15 minutes past our normal end time. But hey, now your homework is done for the day, and you have some time to move on. So I'll hang around here for a couple of seconds if anybody has any questions. Otherwise, that's it. Have a great day, folks. Thank you, guys. Bye, folks. Yep. Hey, I got you, man. Yep. Nope. Nope. Those are all for you. Yep. Have a good one.